Mercury grows larger with every image Messenger sends back. After years of travel, the destination is finally filling the frame. But the spacecraft is not relaxing into arrival. It is doing the opposite. As it closes in, Messenger stays locked in an unusually rigid orientation toward the sun. One side is flooded with light, the other remains in shadow. Engineers watch thermal limits as orbit approaches, knowing that a decade of work can disappear with a single mistake. The closer Messenger gets, the less useful normal spacecraft thermal design becomes. Reaching Mercury is no longer the main challenge. Surviving the environment is. Near Mercury, sunlight can exceed roughly 11 times the intensity experienced near Earth. Messenger entered the strongest sustained sunlight environment any planetary orbiter had operated in. The spacecraft almost looks like it is carrying a permanent shadow with it, dragging darkness through a sea of light. That shadow is not cosmetic. Every exposed component becomes a potential failure point. A small change in orientation can suddenly turn safe hardware into overheated hardware. And the most unsettling part is that arriving at Mercury makes the danger worse, not better. The planet is finally within reach, yet the real threat is only beginning to reveal itself. Thermal simulations begin painting an uncomfortable picture across the Messenger spacecraft. Heat spreads over surface after surface. Areas that look acceptable at first keep getting hotter, then hotter again. The problem is not a burst of heat. It never stops arriving. As engineers review the numbers, one design option after another starts disappearing. The obvious answer seems simple: build stronger hardware, use tougher materials, make the spacecraft harder to damage. But the thermal maps keep moving in the wrong direction. Solar energy is arriving continuously, every moment. Messenger remains near Mercury. Heat accumulates faster than it can escape. Even durable materials have a limit. They keep absorbing energy, and the longer the exposure continues, the more that energy builds. The result shows up visually before it shows up as a failure. Surfaces keep heating regardless of how strong they are. Temperatures keep climbing. Time itself becomes part of the threat. That realization breaks the simplest solution available to the mission. Engineers are no longer asking how much heat the spacecraft can survive. They are watching passive survival become impossible. The mission now demands something different. Messenger cannot merely endure the environment. It must actively manage it. Survival is starting to depend less on resisting damage and more on controlling exposure. The spacecraft does not just need to be tough, it needs protection. The answer finally arrives in the form of the Messenger sunshade. A cross-section of the spacecraft reveals the idea. Critical electronics sit behind a protective barrier while sunlight slams into the outer surface. Instead of forcing every component to survive the full intensity of the environment, the design creates a protected region where the most sensitive hardware can remain hidden. As the mission approaches Mercury, the system performs exactly as intended. Direct solar heating is blocked by the shield. One side of the spacecraft sits in blazing sunlight, while the hardware that matters most remains buried in shadow. Then the numbers start looking surprisingly normal. Internal temperatures stay within their operating limits. Thermal systems hold steady. The constant accumulation of heat that threatened the mission no longer appears unstoppable. For the first time, the environment looks manageable. Years of engineering suddenly seem justified. The Messenger sunshade transforms the situation from endurance into protection.
As Messenger
The spacecraft no longer appears trapped in an impossible thermal battle. It appears prepared for it. And from the outside, the result looks almost simple. Sunlight strikes the shield, the electronics stay cool, the spacecraft survives. At least, that is what it seems. If the shield works this well, then the danger should be over. Then engineers reveal the catch. A safe orientation diagram appears, and suddenly the shield looks very different. The messenger sunshade is not wrapping the spacecraft in protection from every direction. It is protecting one direction. The spacecraft survives only while maintaining a precise attitude relative to the sun. A slight rotation changes everything. In simulations and operational reviews, the spacecraft turns only a little. Hardware that was hidden behind the shield begins to emerge from shadow. Areas never meant to face direct sunlight become exposed. Thermal danger zones appear immediately across parts of the vehicle that had been safe moments earlier. That observation collides with the comforting assumption that the shield solved the problem. If protection were simply built into the spacecraft, orientation would not matter this much. Yet mission operations continuously manage messenger attitude to prevent exposure. The spacecraft is not merely carrying a shield, it is constantly positioning that shield. The reason becomes visible across the entire vehicle. Radiators depend on specific orientations. Instruments depend on specific orientations. Electronics depend on specific orientations. The shield blocks most direct solar heating, but only while every major system remains arranged exactly where it needs to be. The consequence is unsettling. Safety is no longer a physical property of the spacecraft. It becomes a procedural requirement. Messenger attitude control is now part of the thermal protection system itself. Years of work no longer depend only on strong engineering. They depend on never allowing the wrong rotation at the wrong moment. The spacecraft is protected, but it is also continuously protecting itself. And that makes survival far more fragile than it first appeared. Messenger settles into a stable orbit around Mercury. From a distance, it looks like the mission has conquered its destination. The planet passes below. The spacecraft keeps working. Year after year, the systems remain alive. But the final picture is not really about Mercury. Overlay the thermal geometry, and a different reality appears. The messenger thermal system survives by preserving a strict relationship between the sun, the shield, and the radiators. Heat is constantly arriving, and heat must constantly leave. The radiators can only reject that heat effectively when they remain pointed away from direct sunlight and away from Mercury's reflected heat. That balance never becomes permanent. It has to be maintained. The spacecraft operates for years not by defeating Mercury, but by preserving that geometry every day. Mercury remains below, yet the sun above is quietly controlling every major decision. Orientation, exposure, cooling, survival. Everything traces back to the same constraint. That realization destroys the original assumption. Mercury was never the primary enemy. Exposure was. The mission succeeded because Messenger continuously protected the conditions that allowed it to stay cool. Its survival depended on a fragile operational rule that could never be ignored. Complex systems often fail the same way, not because of the obvious threat, but because of a hidden dependency that must work every single day. There was never a safe side.